Hi, welcome to this video. My name is Phil and I'm a senior lecturer in astrophysics at the University of Lincoln, and I want to use this video to explain how we actually calculate what one astronomical unit is. So firstly, what is an astronomical unit? Well, it's the average distance between the Earth and the Sun, and we use it as a unit in astronomy, astrophysics, because actually it's better than using meters, kilometers, because those numbers can be enormous. So we use the unit of astronomical units because it just makes the numbers a bit more manageable and it makes a bit more sense. Like if I say 2 AU, 2 astronomical units, we know it's twice the distance between the Earth and the Sun. It's a bit more easy to understand than just having some ridiculously large number in meters. So before we do this, let's just define the orbit of Earth. So we have this semi-major axis. And this semi-major axis is essentially half the major axis of the orbit of the Earth if it's elliptical. Now if we go to a circular orbit, the semi-major axis is just the orbital radius. It doesn't change. Or what I should say actually is the distance between the planet and the star, or the Earth and the Sun, doesn't change if the orbit is circular. But the semi-major axis is it's a bit different actually when you have an elliptical orbit. So if we have an elliptical orbit, so it's elongated like this, which is the Earth's orbit, this is a lot more extreme than it actually is. So, I mean, some planets do have very elliptical orbits, but we have this ellipse now, and the major axis is the longest part of that ellipse essentially. And the semi-major axis is just half of that major axis, hence the name semi-major axis. And it's denoted by this letter A. So if you come across that, that's kind of what it means. It's the semi-major axis, half the major axis of the ellipse of the orbit. And the opposite one is the minor axis, which we don't typically use, but that's the the narrowest part of the orbit, the shortest distance on its orbit. Across the ellipse essentially. So we use the semi-major axis as an orbital parameter. And actually if you want to watch up some other videos of how you calculate that, I've got some videos on that as well. So if we know the semi-major axis, let's go back again. We want to find the semi-major axis actually, because the semi-major axis is actually going to give us the average distance between the Earth and the Sun. And we need to actually calculate or find the period. So Kepler's third law can be used to find the semi-major axis. If we know the mass of the star or the mass of the Sun, we would have some other measurement really to get that. And again, I've got a different video on how you calculate the mass of the Sun. We also need to get P, which is the period, the orbital period of Earth. So if we rearrange that, or I should say we take the cube root, what we now need is this orbital period. We've got the others, so G is a constant, and you've got your 4 pi squared, and the mass of the star or Sun, which again, a different method to do that. We need the orbital period of Earth. So one way to get that is by using parallax measurements. So from Earth, if we look at stars in the sky over a 6-month period, which I've already told you is half the orbital period, we get this parallax effect. So on different sides of Earth's orbit, a star that is closer or further away, they appear to move, and this is a parallax angle. So the background stars will appear to move back and forth, and that angle will oscillate over the orbital period of Earth. If it's longer, it takes longer for it to wander, but basically it's a parallax effect. The background stars will appear different in different parts of its orbit. So looking at the arrows there, if you look down those arrows, the background stars are going to be different compared to on the other side. So we get this parallax angle. So your parallax angle will vary during the orbit if you're looking at the same object. And then you've got your time along the x-axis. And to get your orbital period, we would just go one cycle of that. So from peak to peak, measure the time. That would be our orbital period. And that's one way of getting it. There's other ways of getting orbital period, but that's one way that you could do that. And if we do that, so if we get the orbital period, which works out about just over 365 days, we've got the mass of the Sun from another measurement, so just under 2 times 10 to the 30 kilograms. We get this number for our astronomical unit, which I'm not going to read out. It's a very long number in meters. Like I said, this is why we actually go to using astronomical units and other sorts of astrophysical units that we might use as well, like planetary radius or mass. It just makes the numbers a lot more manageable. So that is how we calculate one astronomical unit. Now, thank you for watching. If you enjoy the videos or find them really helpful, do consider becoming a member of the channel. It helps support the channel, and there's extra videos in the member section as well. So thank you for watching.